Next, let's see the magnetic flux density. Magnetic flux density B can be written as B equal to mu naught H, and the unit is Tesla. So we can see from here that the B is depend on the material properties. In this topic, we just only considered that our region to be whether the free space or the vacuum. So the mu naught here is referred to the permeability of free space, equal to 4 pi multiplied by 10 power of minus 7 Henry per meter. In your calculation, the mu naught is a constant 33. No need to memorize. Okay, let's consider a material we have a permeability of mu naught. It has the cross-section area of A. Right, so let's say that our magnetic flux is flowing across this section area, and our flux density is a B, and in the same direction with H, our field. Therefore, we can determine the total magnetic flux M is equal to the integration of B dot ds. So the B multiplied by the surface. Okay, the unit is Weber. Flux M is a total magnetic flux through a surface area S. Right, let's say this is our current source I, and this is our field. Right, so our B is flowing in the same direction of our field intensity, and the surface here is the surface that the field goes through. That means the direction of your surface is also around the field directions. So don't confuse with the surface area. Let's see example 3. The example 3 is basically the case for volume current source. The question is find the magnetostatic field at all regions. You are given, okay, this is a coaxial cable. It has a radius of A and B. Okay, so our current is flowing between A and B, and the volume current density is given by Z in the direction of Z 10 ampere per meter square. Right, so the current is flowing in this surface. Right, so first, when R is less than A, right, when we solve the closed integration of H dot dl equal to I enclosed, when we draw the Amperian loop here, so basically there is no current, okay, inside our Amperian loop. That's why the J dot ds is equal to 0, and the field is equal to 0. Alright, next is between A and B. When we draw the Amperian loop between A and B with the radius R, so when we solve the closed integration of H dot dl equal to I enclosed is equal to J as ds. Okay, so J is given, and the ds is ds here. Okay, between A and B. Right. So is the H is in the direction of phi, and we have a phi component from 0 to 2 pi. Okay, in closed loop, and our dl also in the direction of phi, which is r d phi in the direction of phi. Is equal to the surface between A and B is 0 to 2 pi, and from A to R, our current density Z 10 dot ds, our ds is here, r dr d phi in the direction of z. So we can solve here. So h phi r d phi is 2 pi r, and we have 10. This is r square over 2 because we have r here. So r square over 2 from a to r. And then phi is 2 pi, 0 to 2 pi. So the final solution is our h equal to phi over r in bracket r square minus a square ampere per meter square in the direction of phi. Next, when r is greater than b, which is outside our coaxial cable. So when we draw the Ampere loop outside, so we can see here that we covered all the currents, right? So the closed integration of h dot dl equal to I enclosed equal to j dot ds. So this is the same thing. The h phi 2 pi r is equal to 10. The integration of ds is r dr d phi, so r square over 2. The difference is only our limit is from a to b because we covered everything. Okay, a to b, and this is the same 2 pi. So the final solution is phi over r b square minus a square ampere per meter in the direction of phi.